computer. Yes, thanks. Okay, so the reminding. Okay, so yes, about the protection purposes. Yes, so detect electrical faults and disturbances and protect people and property. And if, for example, we are talking about the property, yes, it means only the property, for example, where people lives, okay, any other things. But for example, for me, if I am part of a transmission line operator or distribution line operator, yes, what do I have? I have transmission lines, I have substations, I have transformers, yes, and I want to protect my transformers, my transmission lines from a fault. So I want to disconnect this fault, yes, from my system, okay, because for example, if I am transmission line operator, yes, I don't care what is going on a high voltage level, yes. If I am a transmission line operator, I am not interested what is going on a low voltage level, because it's not my equipment. But I want to protect my equipment, because if we got a fault somewhere, yes, this fault is dangerous for my equipment. So when I'm making this relay protection, my first idea is, okay, because who makes this relay protection? Okay, if we go from the higher level, yes, from the top, yeah, for example, with the high voltage, yes, so transmission, generation, and so on, yes, and go to the low level where we have people, properties, yes, so domestic uses and so on, yes. So first of all, who are on the top, operators, yes, they want to protect their own equipment. And people on the lowest level, yes, for ordinary people, what I'm living in my flat, yes, with my wife, we want to protect our property, yes, we want to protect our equipment, yes, electric device and so on, from the possible fault. For example, if I got fault with my washing machine, I want to disconnect and to be sure that all other my electricity consumers, such as this my laptop and so on, will be alive, yes. So that's why the idea of on the each level is a little bit different, because each one, everyone, yes, have a little bit different equipment what they're going to protect. That's why we need just for this case understand the logic, yes, the idea. So what are the requirements of protection? Of the protection requirements. So first of all, it's a sensitivity. Yes, we need to detect the fault. If we can't detect the fault, we can't disconnect. Yes, we can't deal with this. So first of all is to possibility sensitivity, the possibility to detect. Second one is the fast, the time of reaction. Because, for example, if it can deal with this fault in several hours, maybe everything will be broken. Transformers, lines, and so on. So time, yes, fast. Selective or selectivity. Yeah, we will talk about the selectivity a little bit closer today. But what is the idea about the selectivity? The main idea is to understand who should disconnect the fault, yes, which circuit breaker should disconnect, which one circuit breaker should disconnect this fault. And in this case, because it goes very close, yes, so which one relay protection should send command, yes, to which one circuit breaker to disconnect, yes, the broken, the faulty element, the faulty unit. Full coverage, yes, so we need to protect all, and reliability, yeah. I don't know, we have discussed it a little bit about this N-1 criteria for the reliability. Do you remember, or maybe you got several information about this idea of reliability, about this N-1 criteria? Do you need to remind this? What do you think?
Yes, Professor.
What does it mean? Yes.
Yes.
Okay, so you know what
No,
does
no,
it
I
mean?
didn't get the question.
N-1 criteria for reliability.
No. I can't understand the question.
Okay, so so this one I need to describe as well. Okay, good. So, and the level of reliability. So the idea of reliability is very simple and very difficult at once. Because if we want to make a very reliable system, for example, we need to make, for example, a backup. Yeah. If we can have several backups, we will get, for example, very reliable system. Maybe some very simple example for an everyday life. Okay, if I have, for example, it's winter, it's a very cold time. I have, for example, no, I don't have a bed. Okay, it's example, yes, a private house, and I have a heating system with gas boiler. Okay,
Mm.
if I got problem with my gas boiler, it means I don't have a heat. It's cold in my house. Yes, I can
Yes.
make a backup device. Okay, for example, I can have two gas boiler, for example, or one gas boiler, one a heat pump. Yes, so if something will go wrong with my gas boiler, I can switch the system to a heat pump and go the heat. So I have a backup device. So I have two devices. Yes, so the
Yeah.
n is a number of devices. It is two. Yes. So if
Yes.
something will happen with one of two my devices, it means that n minus one. Yes, one is fault. Yes, I will got
Yes.
the heating. So if I will have three devices, yes, three heating sources, for example, domestic heating, for example, as well, maybe
Yeah.
I will got a more reliable system, and this is idea. uh, how many backups do we need to have to make a system a reliable system? What is how's enough reliable system? And in this case, the idea is that if we could project and real no, and make a power system with a reliability level of n minus 1, it means that if we lost no minus 1, if we lose
Mm.
any one unit in the power network, it means no any one does it's a digit. Yes,
Yes.
uh, the system could fully fill its task, so nothing will happen. Like
Mm.
in my example, for example, I have a heat pump and I have a gas boiler. If something goes wrong with gas boiler, I have a heat pump, I can switch and got the heating, so nothing will happen. Yes, I will got this heating. This is idea. So the level of backup, it means that if um, I lose whatever one
Mm.
uh, element in power network, any transformer, any generator, any transmission line, any substation, yes, it means that everything will go. And in some time, this criteria was taken like an optimum, yes, because we compare the investments, because for me it's investment in gas boiler, it's
Mm.
investment in heat
It-
pump, and so on. So for any new unit and any new device, you need investments. Yes, and if you can make a lot of investments and a lot of backup, and you will get a very reliable system. But on the other hand, all these are investments. It's not so easy, it's quite expensive.
Mm.
So it's a question how to find this optimum. Yes, and the optimum, as I said, it was chosen to use this n minus 1 criteria. It's still actual, but there are a lot, no, not a lot, but there are a lot papers you maybe could try to find if you wish in the libraries, no, internet, of course, libraries, when people are discussing about is this criteria an optimum. One very famous United States professor wrote good paper with the main idea of this paper, that this criteria n minus 1 is very stupid. So different points of views, but still not of course everywhere, but this because power networks were projected and developed a long time ago, and this criteria is still active and still actual, yes, n-1 about the reliability. But this is about the idea of the whole system, how we make this, yes, and about the philosophy, how what relay protection should ensure for a power network. But for if we are speaking about the relay protection device, yes, of course, reliability is about the possibility of this device to make this all this to detect, to react fast, to react selective, and so on. So to be possible to fill all the tasks, yes. Okay, let's go next about this key terminology. I tried to say some words about everything, and let's go to the selectivity. But first of all, I'd like to say some words about voltage levels, about this transmission, distribution, and private zones, about how we divide this protection. So first of all, let's talk about the top level when we have generators. Yes, we have generators. I use very simple sketch. Okay, let's, for example, okay, but no, okay, we need transformer. Let's be here. Generators, we have transformers. Okay, I'll use a simplest one transformer, two winding. I want to copy paste. Okay, something is not good. Whatever. Okay, so about some different levels. Okay. So here we got generators. Yes, here we have power generators, PG power generators. Yes, as we know, power generators have the voltage level of several kV, and if we want to connect this generator to a power network, to a transmission line, of course, if we're not talking about the big generators, not about the distribution generators, and yeah, so we need a high voltage. Okay, there are several voltage. I don't know. For example, I say, for example, 4, 6 kV. Yeah, no, it's quite ordinary voltage for a power generator, because if you, I don't know what is your knowledge about the electrical machines, but I think you should understand that, for example, if we have a high voltage, it means that we need to have a very good insulation, because voltage, yes, and if we have a good insulation, it means that we have a very huge electrical machine, a very huge device, yeah, because due to all this insulation. So that's why for power generators, the optimum about this construction, how to say,
We need surge protection also.
sorry,
Surge protection.
what does it mean, surge protection?
It is control the losses also. Surge protection.
Protection. I say I hear production. Sorry.
Okay.
Okay, yeah, but yeah, okay. So then, okay, about this protection, we'll go a little bit next. So yes, first let's say about the voltage levels, about this protection levels. So yeah, power generation, it have a mid voltage, yes, but if we need to connect it to the high voltage, so we need a transformer and to raise the voltage up to, Yeah, sorry, I see surge protection. Yes, surge protection. I understood. We need to raise the voltage to a high level. About, for example, for Latvia, it's 100 kV or 330 kV. For Estonia, with Latvia, we don't have. In Estonia, they have 220 kV. Of course, this voltage level depends on transmission power. How much power do we need to transmit and the distance of transmission? Because why do we raise the voltage? Two issues: to decrease the losses, yeah, and to increase the power, because we understood power it's a current multiple voltage. Yes, we can't decrease the power current very simple, because it depends on the wire. Yes, wire construction, wire diameter. Yes, because high current, it means it's heating. All the wires are heated. Yes, and this is quite expensive. Yes, to make more how to say white wires. Yes, they will be very heavy, very expensive, and so on. That's why if we want to increase the transmitted power, we can raise the voltage and to increase this power. This is the first case. And the second test, I said, it's losses. Yes, losses in wires is quite big problems, because all losses, it means that this is expenses. Yes, because electricity is money and someone need to pay for these losses. Yes, so that's two main things. Yes, the distance and the power. This is the high voltage level. For Latvia, we have only two. Okay, I want to these voltages, but the voltage could be more higher. For example, 500 kV or 7 or more.
11,000
Yeah,
kV.
1000. Yes. For very long lines, yes, transmission lines for very long distances. Yes, this could be very actual. There are only several places in the world where use this voltage, but this voltage exists. For Latvia is a very small country. Yes, this so high voltage is not actual. Yes, for us. That's why we use this one, only these two types. Okay, this is about the high voltage. And the number of transmission line is always not big. Yes, the high voltage, the lower transmission line we have, and the lower number of transmission line we need, because we could transmit, due to this high voltage, a very big amount of power. And in this case, the I forgot the word. The word is say increase for this relay protection is very high. Yes. Okay, as we said here, okay, this main requirements, or yes, this was requirements. Yes, so the requirements for relay protection are also very high, because, and in this case, yes, the more expensive and the more reliable relay protection is always used in this transmission line level. The difference in prices for relay protection in transmission distribution line, I'd say the difference is in hundreds. So it's not $100, it's a multiple by hundreds. Yes, so the difference in level is very huge. That's why use different types of relays, because for transmission line it's quite expensive to use such types of such technology of relay protection. That's where transmission line distribution operators use more cheap solutions. But okay, let's talk. So, okay, transmission line, we need to transmit. Okay, we need to transmit, let it be blue. We need to transmit. No, okay, and we will not have so much place. I need to make a short line, yes, transmission line. So this moves, there we got this high level. Okay, let's copy paste this and put it here. So this is the high voltage. Let's write this is high no, sorry, high voltage is here. High voltage. What is more, I'll write here for transformers the winding, transformer winding connection, or in other ways the natural connection. Yes, how the nature, is it the triangle or it's an open star? Yes, or grounded star. For Latvia we use this type. It's quite ordinary way we use this type of transformer.
Delta
Delta,
star.
yes, delta. Yeah, this is delta, or what do you say? Okay, yes, sorry.
This is a delta, that is star connection, yeah.
Yeah, this is star, this is delta. Okay, just
Yeah.
okay. It's triangle. I just translated. Yes, it's a delta. Yeah, you're right. You're right. In English, it's a delta. Yes, it's a delta, and this is star with ground. With ground. Why this is? Why we use this such type of transformer? Yeah, natural connection. Because of relay protection. The relay protection says us what the connection will be the best. Why? Because, for example, if we see the statistic of fault types, yes, historical statistics, which type of faults appears, yes, the first one, so the most the highest probability, yes, will be, no, because the most number of faults is one phase grounded fault. Due to a lot of things, first of all, nature, trees, yes, wind, strong wind, the falling trees, bushes touch it, so, or a flying bird just drop it over the transmission line, any branch. Strong wind, and so on. So most of all, the reason is in nature. And the easiest type of fault to be detected is a grounded fault when we use a star with a ground connection for the transformer windings. The easiest way, because in this, for this connection we have a very high fault current, and if we have a high fault current, it is quite difficult to detect. If we have a delta connection, yes, in this type, we will not have a high current when we have a fault, ground fault, one phase ground fault, and we don't call it a fault. We call it a ground connection if we have a delta. Why? Because you don't have a winding connection to the ground in a delta, yes? In this case, there is no short circuit, yes, between their winding. No, winding is here. Yeah, I maybe like it with. I don't know. Okay, I just. To remind, to be easy, yeah. This one or okay, not so so now is but understandable. Okay.
Yeah.
So what does it mean, a fault? We have a connection here and here, yes, without resistance, yes. And in this case, there is, if we connect these two wires, we will not have a short circuit. In this case, for a transmission line operation, whatever, what voltage level for this power system operation, if we have for a delta phase connected to the ground, it's not dangerous. And the power network could keep operating. Phase connection to the ground is dangerous for a people in a place of connection because there is a so-called step voltage. So, and this step voltage can kill a human or any nature being, yes, so any animal or something who will go who will work around this phase connection to the ground, yes. Nobody cares about animals, sorry, that's alive, but for people it's dangerous. That's why there is a law and limited time to disconnect, yes, this ground connection, this phase connection to the ground in a how to say in a network part with delta transformer winding connection, yes. So the time is limited, so people should find, if there are two ways how to deal with this, or relay protection should detect and disconnect, yes, this line part that has a fault, or people should go and find and to disconnect manually, yes, two ways. But the time, why two ways? Because we have time, because this is not dangerous for network, and this type of fault is quite difficult to detect because we don't have a high current. There are special solutions how people deal with this. These special solutions calls, for example, Peterson coil, or something that sounds like compensated neutral, and so on. But I will not waste our time to talk about this. If Dolgitzer wants, he will talk about this, or you could read in a book that Dolgitzer suggested about what people do with relay protection in a distribution network. But just you to understand that this winding, yes, this choose of winding, of transformer winding connection, yes, is made based on the relay protection requirements. Okay, so this is a high voltage. Let's go to the mid voltage, yes. So because we're talking about, so mid voltage, medium voltage, so, and okay, and medium voltage, you could see here that the winding connection is delta. In this case, because the number, of course, in distribution number of fault is huge, because the number of lines in mid voltage is huge distribution network, and in this case, yes, they need to deal with this. Okay, faults are not dangerous for the network. There could be thousands of faults in this distribution network, and this distribution network could operate, yes, but relay protection or people should deal with this because it is dangerous for people, yes. In this case, we are interested in protection of our transmission line over high voltage devices. That's we use this type of the star connection and with a very high short current. Here we use different philosophy and we use different connection. And the next one is low voltage level. Okay, low voltage level. When we have Okay, some words about, okay, yes, this mute voltage. What does it mean, mute voltage? I haven't written here. It's 6, mid voltage, it's 6, 10, 12, or 35 kV. In Latvia, we have only 6 for rural areas. For now, this number is not big. Why? Because distribution network operator is trying not to use this voltage more. Why? Because the more voltages you have, the more devices you should have. And this is more expensive. That's why we want to keep only 2 types of voltage, 10 and 20. So this and this one. So a little bit they are replacing all these transformers, and 6 will disappear very soon for rural network, for rural areas. Yes, so will be only 10 and 12. 35 if too much. We don't have such consumers for 45 kV. So this is a mid voltage, and the low voltage. Okay, low voltage, it's 1. We have several new types of lines of 1 kV, 1 and 0.4 kV. Yeah. kV. That's why. Low voltage, and here you could see again, we come back to the star connection, and that's why we have in a circuit at the home 1 phase and 1 neutral. Yeah, 0 neutral wire. Yes, neutral wire and the phase. Yes, because the voltage phase to neutral is 230 volts. Okay, that's why. So about the level of protection. So here at this level is domestic. Yes, domestic protection. And domestic protection, what we're using, we use circuit breakers. Very simple. Yes, A, B, C type of circuit breakers, as you know. So very simple, but they are not so simple. Okay, maybe we'll go to from this. Okay, yes. Here we go. Coordination and grading. Okay, so yeah, we have something like this. It's a current and type figure. Yeah. That explains the operation of a circuit breaker. So we have 2 separate types of protection into one housing. And these 2 types we call inverse time and defined time. This part is inverse time. What does it mean? The time of disconnection depends on the current level. Current level is here. This is the coefficient to a nominal power of a circuit breaker. If current is, for example, here 5, okay, not 5. Let's find a little bit. Okay, let's find, for example, this red curve. Yes, because it's the same. If the current is 15 times higher, more than the nominal of the, for example, if I have a circuit breaker of 10 amps, so 15 coefficient, it means 150. I have this time of disconnection. If I have this 5, it means 5 multiple to a nominal current, so 5 multiple 10, 50. Yes, I will got this time of disconnection. So this curve depends, yes, on the disconnection time depends on the current. Why this curve exists? Due to the history and the use of fuses. Yes, because the first okay, the very simplest and the most reliable way how we could protect from a high current is to use a fuse. because if we have a high current fuse, yes, because it's a physical element without any moving parts, yes, just deal with this current. If current is higher than the fuse could keep, it's over, and the circuit is disconnected, yes. So, and the fuse construction is a piece of wire, yes, a piece of copper, and the higher current, the faster will this copper part will be destroyed, yes. So this curve is typical for any fuse, yes. And if we have fuses like a protection device, we need to make the operation of circuit breaker selective to the fuse, yes. So these two types should be selective. And what we see here, for example, if a relay device use a defined time operation type. What does it mean, defined time? Okay, if we have a set point 5 amps, it means then if a relay protection device detects a current higher than the 5, no, bigger than the 5 amps, it says disconnect. So the operation is like this: we got a high value, we say disconnect, and whatever the current will be, it will be 50 amps or 150 amps. The value is higher, it means the disconnect without any delay. Yes, no. So that's why this is such type of operation curve, so which calls the defined time operation curve. So yes, defined time for a protection device. Yes, when we have a protection device, mechanical, electromechanical, or digital, whatever. Yes, so we got the input information about the current value and we make a decision, yes, to disconnect. And whatever will be the current, if it is higher than the set point, disconnect. And the inverse time for a fuses, when the disconnection time with Cooper inlet destroying time depends on the current value. That's why for ordinary circuit breakers, yes, yes, for ordinary circuit breaker like this, yes, devices, we have two types of operation curve. This type is inverse time, yeah, to be possible, yes, to synchronize this circuit breaker to a fuse, yes. And this type, if current is too high, not to wait and to disconnect it without any delay, yes. So this we are waiting, yes, we have a current and we have, for example, it's 5, okay, this point is, for example, 3 times more than the nominal power. If we have nominal power of 10 amps, it means that if we have a current of 30 amps, we have 3 seconds, and in 3 seconds it will be disconnected, yes. So but if we have very high current, we don't need to wait and we can disconnect without any delay. So this is how the modern these type circuit breakers, for example, operates, and this is how the relay protection, digital relay protection devices operates as well, because it is important to have a possibility to make a selective operation with a fuse. So this one is, how to say, the best, yes, without any additional delays, but we need the possibility to make a selective operation with a fuse. That's why the current protection device, if current protection relay, should have both these two curves. And about this selectivity, okay, we started to talk about the selectivity, and we need to come back here to this slide and to say some words about the selectivity and selective operation. Okay, here, for example, we have a distribution network, and we have this because there is a closed loop. Yes, it's a quite typical rural network when we have different substations, and all this is closed like in a loop. And we have a fault here. In this case, we need to disconnect from the network the fault unit. In this case, it is a line, this line. We need to disconnect only this line when we have a fault, yes, to save all other network from a fault. In this case, relay protection devices, yes, that protects all the units in the network, all generators, transformers, lines, buses, and so on, yes, should operate in this way that only this line will be disconnected. So the relay protection that operates on this, okay, I try to say different words. Relay protection devices, which task is to protect this line, should operate first and should disconnect this line from the network. This will be the selective operation. In case if any other relay will say disconnect any other element, this will be not selective operation. For example, like here. Okay, so there is a fault in the network, a high current. How current flows? No, very simple, from the generators, because generator is the source of a current, yes? So fault is here, high current flows from generator here, from generator here, from generator here. And it means that relay protection devices that protects this transformer, this line, this bus, this line, this transformer, this bus, this generator, yes, they all see the high current. But only this relay that protect this line should operate first. All these relays that are red should detect the current because this current is high. It is a fault current. But operate should only these two. No, okay, relays that protect this line. All others should detect but should wait. That's the idea of selective operation. Because if we disconnect all these breakers, yes, power breakers that are red, we lose everything. No, this is written here. Yes, we lose this power network because we'll disconnect all the sources, yes, of electricity. This is a bad situation. So we don't need to make such a protection. That's why there is a question how we could say to relay which one should to operate first, which ones should to operate second, and so on. In this case, why this selectivity is so important. So let's start from the easiest way about radial network. When we have the power supply only from one side, this is more easy. This is simple. We have a distribution network, not due to this current. Here we have fault current values. K2, you see E K2. So I say letters in Latvian. I'm sorry. Sometimes this happened to me. So this is IK2. Yes, that means this letter K and the number says what type of fault do we have. Because what types of fault do we have? It could be three-phase current. So three phases are connected together. This will be K3. If we have two-phase current, yes, this is the K2. if we have one phase current, no phase to ground, because one phase could be, how it could be fault, only with ground connection, will be K1. So for these types of current or fault current, we have this letter. So I, it means a current, and K with a digit says what type of fault do we have. And here we see these two-phase fault values. If we have here, here, and here. Here we go 1000 amps, 700 amps, and 150 amps. Yeah. And here we got the relay, which task is to protect this this line. Okay, it's not transmission, but it's mid voltage, but okay, this line to protect. And the first question from here is, what should be the current set point for this relay? And you have to choose, you have four variants: 150, 500, 700, and 1000. What do you think?
1,000,
Why?
because we have,
Why do you choose this one? What
because
is your idea?
there will be some losses,
What types of losses?
the transmission losses.
Okay, so you have a line, yes? In
Yeah.
different places, yeah, we will got a different current value. Maybe I need a little description for this. Maybe, okay. Let's imagine, okay, we're talking about this. We have a line, just a transmission line. And we have I want to let it be black. How to, this is for, okay, let's use, okay, this is, let's use something. This is transmission line. To be easier, let it be 10 kilometers, for example. Yeah. Transmission line, just an example. And this is current, fault current, okay, whatever, let it be K2, yeah, two-phase current. Values, here it is. This is the distance, yes, distance. Distance, so this is a value, yeah, amps. What does it mean? Because a transmission line, it's a resistor. It's a big resistor, yeah. And if we have a fault, for example, here, so it means that in this place, we have this phase connection. And it means that from a source, yes, there is a source. Yes, to there is a resistance. Okay, L wrong. Let's full resistance, Z. We have resistance, yeah. And if we use the Ohm law, yeah, when we have voltage drop here, and it means that we have a resistance, voltage drop, and it means that current value is here. If we have a fault here, because E is equal, yeah, we have, okay, what color? This Z, yeah, this small Z.
Voltage.
Sorry?
Y is a voltage, right? Z is a voltage. Resistance.
Sorry, Z is resistance.
Okay.
U is a voltage.
Okay.
Z is resistance because we have R resistance, we have X resistance, and Z. It's a classical triangle. We have active resistance, we have reactive resistance, X, and we have Z, full resistance. Full resistance. So Z is R plus J, no, X. So it's active and reactive resistance, yes? That is a full resistance. That's why I use this, because we have active and reactive as well. So yes, so we have a small resistance, yes, of wire, of a line, yes, and the current is higher due to the Ohm law. Very simple. Voltage here is the same. The distance to the fault smaller, bigger, the resistance to the fault smaller, bigger, and as a result, that is how change the current value for if we measure here, yes, if we measure, okay, here we have a relay protection device, yes, here we measure current and base it on the place where we got the current, or sorry, the fault, yes, we'll see the different current. So the closer we got the fault to the energy source, yes, so it means that we will have the higher fault current value. And we have, if we will have here at the end, yes, we'll have a smaller value. As we see here, yeah, this is the current measurement. If we have okay, if we have here, we will got the value. If we have the fault here, we got the value of 1000. If we got the fault here, we got the value of 700. And if we got here, we got the value of 150 amps. That's what here is. And the question is still the same. What set point for a current protection do we need to have if we use this defined time? Yes, this current protection relay. So if the current is more than the settings, yes, we'll disconnect this line. What is the idea of operation? We need, first of all, to detect this current and to disconnect. Current of 150, is it a fault? Yes, it's a fault. Is it dangerous? Yes, it is dangerous. So we need to choose a set point to be possible to detect every fault current. That's why we need to choose this one. Because the lowest value is here, this. We need to protect this line from this fault as well. This is the first case. The second one is this. The second one is this. Okay. The same structure. We have a radial network. It means that we have a supply from the top. All is in line, yes, and here we have a feeder, some loads, and so on. And for, as I said previously, we need to protect every device. And here you go, relay protections, yeah, for here we go 1, 2, 3, 4, yeah, that protects, each one protects its how to say, its own unit. Yes, this one for transformer protection, this one is for this transformer protection. Yes, so here we go in line. Yeah, what is the idea? Okay, I just understood that this example is too difficult. Maybe we need to just to use a little bit something more easy for you. Okay, let's use something different. Okay, I will use this drawing, just this drawing. Okay, this just not to be confused, I delete all of this, what I got. Let's use something like this. Let it be blue. Let it be blue. And let's say, okay. Let it be more simple example, like we have only 2 transmission lines and we have loads here, here, and here. And like it is in this example, yeah, this one relay protection for each line. Here we have a breaker, power breaker, and we have a relay protection current relay protection. I write CP. CP, current protection relay, yeah. We have 2 lines and 2 relay protections. And let's choose, let it be, for example, the same values, like it be KE, K2 here, E, okay, not smooth, let's E, let's write I, K2 700 it was, and E, K2 1000, let it be here. The question is, you need to choose set points for CP1 and CP2. What will you choose?
The
CP2
CPU.
should, the idea of relay operation, CP2 is protection of line 2, CP1 is protection of line 1. What will you choose?
For the set point, right?
Sorry?
For set point, right?
Yes, what current set points will you choose for each relay? Yes, for CP1 and for CP2.
CP1. Hello.
Yeah, I'm here.
Yeah.
Yeah, what will you choose? Yes, you say CP1. I'm waiting
Yeah.
for the value, for the set
150.
point value from you.
150 amps.
Okay, let's write 150. And what is for CP2?
For CP2, 700.
100? Okay.
700.
Okay,
700.
let's write 100. Okay. You're almost right. Almost. But this two-phase short current with a value 150 here, yes? This means that this, okay, if we see the 3 types of fault, EK3, EK2, is a fault to face-to-face, yeah? I say it's a face-to-face types of current or fault, yes? Because we have face to earth, it's standard, yeah, they write in all the manuals, face to face, face to earth, yes, so use these types of these names. So this is the low, of course. If we have only 2 phase, yeah, we have a lowest value of fault current. In this case, when the current appears, if we see the EK2 is 150, it means that is the lowest value. Because if you choose 100, yes, this could be a consumption power. So these consumers could consume 100 amps. So, and you know that minimal short circuit current, the fault current is this one. So this is not good. This is not good. We need to use 150 as it is here. And here we use the same one. Why? Because when we have a short circuit here, this relays detects the current and this one detects the current. And this is good. Why? Because in the case of trouble with this relay with this power breaker, because all they are devices, they could be broken or something else, yes? And we can't keep the fault. That's why this relay CP1, because this relay detects the fault, will disconnect the fault from the other network. So the relay CP1 can deal with this fault, and this is very good. But the question is, which one should be first? As we discussed, the selectivity, the less selective, this one should be first. And if this one can't deal due to any issue, yeah, this one should disconnect the second. That's why we have a second option like a time delay, delta T. We have two settings for a current protection. The first set point is a current value. And the second set point is a time delay due to the importance of selectivity. So we need to make a selective operation. That's why we need any criteria, yes, to separate operation of these two relays. That's why we use a time delay. For this, we could use time delay 0 because this one is the last. And for this, we could use a time delay of half a second. If this relay will not do, or will do nothing, to be correct in English, will do nothing due to this time, in a time of half second, this relay will disconnect these two lines. Yes. If this relay will operate immediately and will disconnect this line is disconnected, fault is disconnected from the network, the fault current disappears, and this relay will not see the short circuit, this fault current, and in this case will not operate. Very simple. So these two relays could detect and could disconnect, but due to the time, we could make this selective operation. Is it clear?
Yes, Professor.
So yes, we use one more criteria to make this selective operation. This how it works. And what I want to say more. And in case, okay, if we have a short circuit here, it means that the current goes this way, and there, in line 2, there is no any fault current, yes, because current goes from the source to the fault place. That's why this relay don't see this current, and this relay will disconnect line number 1 in a time half a second. This is the idea how the current relay are made. This is the main idea, how we have two set points, current set points, with the idea to use the lowest possible set point to detect any fault current in any place, any place in line, to be correct. We'll discuss this a little bit later, but for the beginning, it's okay. And the second one, a time delay, just to make the operation selective. This is the idea. Okay. If everything is clear, we could go to the reclosing automation, because for reclosing, for the beginning, this information is enough. Next time we'll start with this point and we'll go next with the current relays, because the current relay is the simplest one, and go next to the directed current protection, to the distance protection, to the differential protection, something like this. Of course, we'll not go deep inside, yes, all these difficult relays, because I decided for you to make tasks only for distribution network, but to be knowledge about all of this, how it operates, we'll a little bit discuss this. Okay, so this is what you need to know about relay protection if we want to discuss the reclosing. The reclosing automation, I need to find where is the reclosing. Reclosing is here. Okay, reclosing is here. I'm sorry again, this is in Latvian, but I use only figures. Only figures. Yeah. Okay, first of all, what is a reclosing automation? What is the idea of reclosing automation? No, it's very simple. If we have a fault, yeah, in line, this fault could be temporary. For example, due to the strong wind, any tree or any branch of the tree just connected a wire, yes? And in several seconds or in milliseconds, this branch, for example, burned up and was destroyed. Or, for example, due to this wind, yes, the branch was just was touched a wire for a millisecond, and this is all. So in case when the fault is temporary, yes, we need a possibility to renew the connection, because first of all, if we detect the fault, we don't know is it temporary or not. Yes, we need to disconnect, we need to make an action, because fault is very dangerous. But we don't know temporary, not temporary, and we need any solution to test was it temporary or not. Maybe we could renew the connection and everything goes okay. And this automation calls the reclosing. How this reclosing operates? There are two possibilities. This is a bus, this is a Q socket breaker or power breaker, this is a line, yes? And this is relay protection. No, in Latvian it is RA. Relay protection, when it detects the current, the fault, says, no, gives a command to the circuit breaker to disconnect the line. And in this moment, it says to this reclosing automation that I am disconnecting the line, please try to connect it back in. For this, there is a time delay, of course, yes. So to be sure that after the disconnection, all the air deionization will go, because you understand, if you have a high voltage, the disconnection with a high current is quite complicated, because we have these lightnings and so on. So this is quite difficult, yes. And for you, breaker, it's difficult, and we need some time to wait to be to let this to be sure that this breaker is ready to operate next. Yes, that's why we say to this reclosing, okay, to be ready to connect it back, and in some time that is set for this automation, it gives a command to the breaker, please connect the line again. And the second idea, to idea how this could be, relay protection says to socket breaker, please disconnect, and if we detect that the circuit breaker is disconnected from the circuit breaker contacts, yes, this automation starts. It's time to say, please connect the line back. This is the idea. But when we connect the line back, so make the reclosing, there always a possibility that we still have a fault. And it means that we are connecting a fault to the power network. And this is dangerous as well. And we will got again the high current value. What should we do in this way? How we make to this all of this operation more safe? How to make this time, yes, the fault current time lowest as possible. Because as I said here, for example, if we have in line a lot of current protection devices, yes, we could have a quite big time here. For example, we saw here, for example, it's a part, you see here time, yeah, 0.2, 0.5, 0.8, 1.2, and so on. Yes, so we could have a quite big time delay, yes, for a current protection device. For example, 3 seconds. So it means, yes, that we detect the fault, we are waiting 3 seconds, disconnecting, reclosing says connect it back, relay protection detects again the fault, relay protection waits again 3 seconds and disconnects. So we have double time, yes, of a fault current, and this is not good. That's why there are some things for reclosing, how we could decrease this time, and we will discuss some types of reclosing. Okay, let's use this feature. And I forgot to say one more thing. We discussed this selectivity and selective protection. This is S means the selective. So this selective current protection here, selective current protection, this is a reclosing, and here is additional unselective current protection. I forgot to say some words about unselective current protection for you. Okay, I need to make back the draw, the feature, how the fault of, let it be black, it's current, let it be, this is the current, this is the current, for example. Okay, what is the thing, what is a cup of tea here? If we compare, of course, yeah, the high value and the low value of fault current. Just using the same scheme, 1000 and only 150. The current value when we have a fault in the beginning of the line could be very high. And of course, the higher value we got, the more dangerous this current is. But as you saw again, for example, from here, yeah, we could have a quite high time delay, because the philosophy, this one, the closer to the last consumer, for example, like it is here again, we have the lowest time delay, and here the closest to the current source, to the power source, we have a higher time delay. In this case, we have a big current and we have a big time delay. This is not good. This structure, this philosophy operates good, but only one moment, when we have a high current, a fault very close to the source, we need to wait because we make a selective protection. In this case, we could use an additional one more relay. No, we could put here one more relay. I call it just CP. Let it be. Without time delay. In other words, unselective protection. Okay, let it be CPU. Unselective CPU. Let's call it CPU. Let's call it CPU. Yeah, unselective current protection. Just with idea, when we have a huge current, fault current, to disconnect without any time delay. So it has a set point. I say set point 1000. Yeah, and operates only in case when the current fault will be high. So it will protect only, for example, this part of the line. Just when we have the very high current value, not to wait and just to disconnect it immediately without time delay. So delta T is 0. So this is the idea when it is possible and when it is good to use unselective protection with cooperation with a selective protection. Is it clear?
Yes, Professor.
Of course, there is only a one power breaker, but we have two protection devices. Yeah. In this case, let's go back to this scheme. When we have a lot of lines, yeah, radial lines, so all they are serial line, no, wire, yes, line 1, line 2, line 3, yes, and so on, with loads. And here we have a current protection, ordinary current protection, selective current protection, yes, with its time delay for line 3. Here we have a selective protection for line 2 and selective for line 1, and additional unselective for this case when we got a very high current protection, just to disconnect this. But if we have a reclosing automation, we could use this current protection device a little bit different. A little bit different. And here we could see, okay, the scheme, how it operates. Here is current. Here we got this one is for current values, and this is for time delays. And here you could see that it is written, yes, the unselected protection time delay is 0. Yeah, no, it's the lowest one. So it operates immediately, but you see here the set points, current set points for each relay. For example, this one is 150. This one is 700, and this one is 1000. Why? Because there is a little bit different types, but whatever, this could be the same. 150, 150, 150. So this is a little bit different case, so don't mind. The main idea here is that the lowest current set point is for the unselective. So here we use this unselective just to protect this case. Yeah. But here unselective will have the lowest possible set point, lower than this 150, for example, 145, with the idea to operate first. You see the time. So this one always operates first. Why? Because we have recloser. And the idea, as I said, we want to have a double time of delay. We're trying to decrease this double time of delay for the reclosing. That's why the idea is that this unselective relays always operates first and disconnect. Yes, all these 3 lines. Recloser connects it back. And if the fault was temporary, everything is okay. If it is not temporary, it is continuous. Ordinary selective automation will do its work. So this protection in its time will disconnect this line number 3. So the idea of use of this unselective protection with the lowest set point is if we have a recloser, whatever, we could disconnect everything because we will try to connect it back. And if this reclosing will not be successful, the selective protection will disconnect only this line number 3, and we lose only these 2 loads, T3 and T2. So the recloser gives more possibilities for relay protection, for the current protection operation. Yeah, this is of course not good because for the first time we disconnect everything. Yes, but this is again due to the expenses. We have only one unselective protection. We have only one recloser, only here for Q1. And in this case, we could make this quite cheap project, yes, of relay protection with the reclosing. As I said, we could use, for example, recloser for each power breaker. Yeah, but this is more expensive. So that's why we are here going through all the interesting use of the reclosing, how this reclosing could help and how it could be used with its advantages and disadvantages. Yes, so this is the first way of use, how this reclosing could be used. Okay, let's go next. The same idea, 3 lines, but here more expensive, more expensive scenario when we have a recloser everywhere. We have recloser everywhere. Okay, how we could use this scenario? Okay, it was how we use this scenario if we have recloser here. Here we could try to use a very, no, not a very, but interesting solution. We could try to disable time delay for selective protection. So not to use an unselective protection, yes, but to use a possibility to disable time delay. How it works? Here we got a fault and relay protection, selective relay protection of line 2 in delta, it's delta, no, it's delta t. So with its time delay, disconnect the Q2 and this line, yeah. Ordinary scenario, but we know this protection knows that there is a fault, and we are going to run a recloser with a knowledge of a fault, with hope that it is temporary, but with a knowledge that there is a fault. And in this case, if we know that there is a fault and this relay protection should disconnect this line, yes, we disable time delay for the recloser operation time. So this current protection disconnected the line, we run a recloser, and for this time of reclosing, we'll disable the delay for a current protection. So in case if we connect this line back and there is a fault, this relay protection will disconnect this breaker immediately. Is it clear?
Yes, Professor.
So yes, we only disconnect time delay of a relay only for a time of recloser operation. So this how this could be used, yes, not to wait again this time delay because we know that there is a fault. This one, okay, there is one more scenario with more complicated. As I said, the first one was the cheapest one, how we could use a recloser. Every next will be more expensive solution, but more advanced. Here we got one more, the same structure, the same scheme, but we have more relays. We have everywhere selective protection with a recloser. No, there is an addition of voltage. Is there voltage or no, but it's not interesting for our case. And we have everywhere additional unselective current protection, selective and unselective. The idea, it is like in a first scenario, then the unselective protection operates first and disconnect, and then selective protection, if the fault current is still here, it is continuous, current protection will disconnect selectivity. But in first scenario, we got only one unselective protection for Q1, and in any case, we disconnected only the Q1. Here, we disconnect all three at once. You see, this is the time of, again, the time and the current of unselective protection. Sorry, this is a little bit different scenario. Sorry, here, no. We have difference in an unselective protection current settings. This is another scenario. Yeah, this is okay. This is This is a combination. Sorry, I was wrong. This is a combination of the first and the second. So this is the idea that we disconnect with unselective protection without any delay, connect it back, and then for the time of the reclosing, selective protection time delay is disabled. So we use a combination of first and second type. In this case, we are not waiting before reclosing and after reclosing. So the best idea. So we keep here the selective operation. Okay, of course, all of the power circuit breakers are disconnected, but for a short time. And at the end of the operation, yes, only the selective protection disconnect line number 2. But we don't have a time delay before reclosing, and we don't have time delay after reclosing. Yeah, but in this case, we need to have a very complicated protection. We need a recloser everywhere, we need a selective protection everywhere, and we need an unselective protection everywhere. So yeah, and we have here one more type, but this is not good, but maybe it could be interesting for you. Why? Because it is mechanical. The idea of the reclosing is based on the spring. How it is in English? Spring. I forgot. Is it spring? Spring. No. Yes, it is spring. Yes, based on a spring. So yes, we have kinetic power for a reclosing for a power switch in a spring. Yes. Yes, it's spring. Yes, it's right word. So what is the idea? The idea when we don't have enough power for a power breaker, yeah, to be ready after the reclosing. What is the idea? If you have a substation, in case of any fault, you have batteries on a substation to make the substation operation, or the relays to operate power breakers and so on. But in a very cheap solution, there could be problems with this batteries, and we have a substation without batteries, and we have electromechanical relays that don't need a power supply. Cheapest solution. In this case, we have a limit for the reclosing. What is if we have a fault, we disconnect from the line, our substation is without power supply, and the only way the power breaker could operate is a mechanical power from a spring. Yeah, so via electrical motor, when we have a power supply, we how to say, store this mechanical energy into a spring. Then in case of fault, this spring gives enough kinetic power to disconnect the line. No, I think it is clear. In this case, when we have this only spring energy, and we don't have any power for additional reclosing, there could be one more type of operation when we use serious reclosing. Very, I'd say ugly way of reclosing, but it is due to due to very cheap solution without investments. So what is the idea? The idea that here, okay, we have a serious reclosing. We have an unselective protection, the cheapest way, unselective protection everywhere, and we have a mechanical reclosing everywhere. But here we have a power of reclosing once. Here we have power of reclosing 2 times, and here we have power of reclosing 3 times. No, kinetic power. So in case of fault, unselective protection disconnects everywhere, and recloser connect back this, and this, yeah. But due to this recloser could operate only once, yes. In case of continuous fault, unselective protection will disconnect this line and it can't be reclosed anymore. In case when we have fault, for example, here, again, everything was disconnected, and for the second reclosing, this one and this one goes back, and this is over. So the idea that we had every time disconnected everything and trying to reclose everything while we have enough power for the recloser, mechanical power. So that's why there is possibility of 3 times disconnection, sorry, 3 times of connection back, 2 times 1 time. And this is then we are disconnecting, connecting back, disconnecting, connecting back. But due to this series tries, we make this selective operation. This is very ugly structure, but very cheap. We use only unselective protection and recloser. No, okay, it is power breakers with this mechanical power, mechanical spring power. So, and to reset the system, people should go and yes, and to how to say, reset this spring for every power breaker. So this solution could exist as well, but as I said, this is quite ugly, but because we're disconnecting, connecting back, disconnecting, connecting back, disconnecting, connecting back. But it's quite simple. It could operate with electromechanical relays without any supply on power substations and so on. So this solution exists, could exist, yeah. And one more scenario what I would like to show you for today about the reclosing. This one is very actual for today and could be more actual in the future. The idea is very old. No, okay, it's idea very old for my country, but for the future it could be more actual, because when our power network was developed, people were not calculating money so much as for today, because in Soviet time, if they had a task, yes, they needed a solution for the task, and the expenses was not the most important thing for solutions, yes, because there was another philosophy of life. For today, expenses is almost the most important, more important than the reliability, yeah. And this case shows how we could use more cheap breakers for power, more cheap protection for distribution network, and how we could, for example, save money to make it less investments. So what is the idea? Here we see the part of a transmission line. Here we go transmission line. Here we have a power breaker with a selective protection and recloser. And what we got here? Here we got feeders, and here we got a load break. So if we compare different devices, different breakers, there are two main types: power breaker and load breaker. Power breaker is a device that is possible to disconnect a fault current, a short current, a current with a very big value, thousands of amps. Load breaker, its idea only to disconnect a load from the network. So its current is 10, 12, 100 amps. It is not possible to disconnect short current due to more cheap construction. And the idea of this scheme is not to use expensive power breakers, but use only load breakers, almost. And at the beginning, at the start, only one power breaker. What is the idea? In case when we have a fault, like it is here in this scheme, we need to protect the transformer number one, yeah, from the fault and disconnect this transformer from a line one. But here we got only a load breaker. This breaker could not disconnect a fault current. What to do? This relay protection detects, it's an ordinary relay protection for transformer, it detects this current value and says to this special device, this device, it's an artificial air connection. So we have a metal piece that, in case of command of this relay protection, connects this to the ground. So we make by ourselves a earth fault. Here you could see. Why? Why do we need this? Because we need to make a big fault current value to run this current protection. So we make a big current value to run this relay protection and to disconnect this power breaker. When we disconnect this power breaker, we lose voltage and of course current. Due to this current pause, so time without current, we disconnect this load breaker and then recloser connects this power breaker back. So the idea to make relay protection makes a big current value to run this relay protection to disconnect this power breaker to be possible when the supply is off, disconnect low breaker and then recloser renew the supply, and this will be disconnected. Is it clear, the idea?
Yes, Professor.
Yeah, so quite actual scenario how we could use more cheap devices, yes, in a distribution network, and how it is possible to save money. So recloser gives a lot of interesting solution for protection. Okay, I think it is enough for today for recloser, for one more type of automation, how power system could operate, because reclosing is quite important because it keeps power network in operation. because power protection, relay protection only disconnects, but we need to keep our network in operation, and recloser helps us to do this. Yes, to keep, not to let, how to say, the deficit in power network, not to use such type of under frequency automation, just to connect the lines. But sorry, I forgot. Not all. I forgot. It is, yeah, I forgot one more thing about the reclosing automation. A few words I forgot. Sorry. Yeah, but very important few words. Very important few words for the reclosing. This is okay. Let's see this scheme. Yeah, reclosing, everything what I said is good, but I forgot to say one more thing. If we, where it is, okay, use, no, not use, if we are trying to make, for example, reclosing for such type of network, okay, if we are talking about the transmission level, yes, high voltage, when we have transmission line with high voltage, yes, that connect several parts of power network and so on, we have a little more complicated requirements for a reclosing. Why? Because, where it is, okay, it is possible when we are disconnecting a transmission line with a high voltage, we are separating different parts of a united power network. In this case, for a time of disconnection, power network as a united unit does not exist, or maybe we have only two transmission lines that separate different parts and we disconnect one, so it means that the connection of two parts of power network is weak. For this, what is going on if we have separate in different parts power network? What is going on with electromotive force of the united generators in each part of the power system? I need a drawing. No, very simple, but for example, it's an electromotive vector. Okay, so time moment one. In every part of power network, they are synchronous, they are rotating, yes, with frequency of 50 hertz, yes. And everything is okay. But when we disconnect the transmission line that connects different parts of power network for these several seconds, in one part of power network, as you saw, for example, in your laboratory, in first part, we could have maybe an overpower. And the second part, we could have a little deficit. That means that for this time, electromotive vectors runs faster here. And for second part, it's a little breaks down. And what we got? We got two asynchronous electromotive force vectors. And if we run a recloser here, just at once, socket breaker for one part, socket breaker for second part, and every line from here, for example, yeah, at once run the connect here and connect here. What is going on? Because we have an angle here, they are not synchronous. we'll got this resulting electromotive force. As a result, a high current value that is dangerous. That's why we can't connect it back if we have this angle. We only can connect it back when they are synchronous. Okay. That's why the reclosing for these two sides, reclosing operates a little bit different. First of all, this is a little scheme how it operates. First of all, we connect only one power switch, no, breaker, yes, back, to get voltage here and from here. And we are monitoring these two vectors, yes, and gives command to connect the second one only when they are synchronous. So the reclosing, yes, for this type, when we have a loop, when we have connection of several parts of power network, yes, could not happen due to the angle between. We could wait, and without success. They are not synchronous, still not synchronous, still not synchronous, because they are rotating, yes, they are both rotating. And we are just waiting a moment, then they go close together to connect it back. That is the case what I wanted to say in several words, that the reclosing for two sides, reclosing, yes, is quite more complicated when we are talking about this transmission line, when we are connecting huge powers of power network. So yes, this reclosing is a very complicated thing, not when we have a serial connection. Okay, now it is all.